So let's look at some graphs of some inverse functions, because we do have an interesting symmetry that occurs when we have a function and its inverse. And it just goes back to the fact that x and y are switching places. Here's an example of a graph and its inverse. We have the blue line is f of x, the red line is f inverse. And then there's a third line graphed here that's y equals x. Okay, and what happens is if you take those two functions, the function and its inverse, and graph them, you get symmetry over the line y equal x. And that's just the way that it works out with the x and the y switching places. This point a1, b1 right here, if you switch the x and the y, you get b1, a1, which is over here. And then that same thing happens, A2, B2. You know, if we were to put numbers, like maybe this order pair is actually 1, 3. When we switch it, we get 3, 1. So you can see if we went to the right 1 and up 3, well then over here we would go to the right 3 and up 1. So you can see those two points would end up with that symmetry there, okay, straight across that line. So so that's what we get, symmetry over the line y equal x. And so if we wanted to, use that to draw the inverse of this function right here, I think that's pretty simple. We've got -2, 1. We just need the point. If we switch the x and the y, -1, -2 is right here. -1, 0 becomes 0, -1. And then 2, 1 becomes 1, 2. So we get this sort of graph right here. And again, the line y equal x is this line right here. And so you can see that symmetry across the line y equal x that happens there. And this is really good because you can use your calculator. If you have two functions and you want to know if they're inverses, you can actually graph those two functions, and then the line y equal x will be 3 separate graphs. And then you should see that, okay, based off of the picture, is that symmetry there? And if it is, then yeah, those are inverses. So that is one use of this, okay? Now the last piece for these inverse functions is to say, okay, say we've got a function and we know it's 1-to-1. How do we find its inverse? Okay, we've got a 1-to-1 function, but we want to know what its inverse is, and that's what these notes right here are getting into. I'm going to skip on down to our steps. There's just 2 steps involved. And the first step goes back to the fact that when we do the inverse function, the x's and the y's switch places. Okay, so what we do is in our equation, we replace x's with y's and y's with x's. So we switch all the x's and y's around. And that gives us what's called an implicit definition of the inverse. You don't need to know that, but just know there's a name for that once we switch the x's and the y's around. But then, it is a function, so once we switch x and y around, the next step is to go ahead and solve that for y to get it into like a function form that we're used to dealing with. So let's see if we can do that. We've got 2x plus 3. We want to find the inverse of that. So we're going to say, all right, instead of f of x equals 2x plus 3, because our first step is to replace x's with y's, we're going to write that as y equals 2x plus 3. Okay, and so the inverse then is going to be x equals 2y plus 3. So all the x's and the y's switch around. And now if I solve this for y, I end up with x minus 3 over 2 equals y, or I could say that f inverse of x is x minus 3 over 2. And just to see, okay, to graph f and the inverse on the same axis, we can do that. I'll just show it to you on the calculator here. So the first one is 2x plus 3. The second one is x minus 3 over 2. And I'm going to go ahead and put the line y equal x on here as well. And if I graph those three, there's my first and my second, and then the line y equal x. Do you see the symmetry? Okay. So this line, one of them is the function, the other is the inverse. Let me just make this y equal x stand out a little bit more so we know that it's not, you know, the inverse that we're looking at. So there's the original function, there's its inverse, and then the line that we should have symmetry over. So it checks out. It's good. The next one is 2x plus 1 over x minus 1. So again, start with y equals, and then do the inverse. So we switch it all around. Make that x equals 2y plus 1 over y minus 1. And this is going to be a little bit trickier because of the fraction. The first thing we need to do, because we need to solve this for y, is we're going to multiply both sides of the equation by y minus 1. I want to clear out that denominator. And so we get, if we distribute there, that's xy minus x equals 2y plus 1. So I'm one step closer. I've got the fraction gone. But notice I've still got x's and y's kind of scattered around. So the next thing I need to do is at least get all the y terms together on one side. So let me subtract. Let's do it like this. Let's put the y terms on the left side. So we're going to get rid of those. The left side is now xy minus 2y. The right side, let's call that x plus 1. And this next step is the trick that you got to know, and that is to isolate the y here, we actually need to factor it out. So we factor out that y, and now we can divide by x minus 2 on both sides. And we get y equals x plus 1 over x minus 2. And that is the inverse. We could also call that f inverse of x. All right. So we got that. Now let's go ahead and graph the original function and the inverse here. So the original was 2x plus 1 over x minus 1. The inverse is x plus 1 over x minus 2. And we should see some symmetry here. There's the original and the inverse. And yeah, it looks like we do have the symmetry over that line y equal x. So that checks out. We know that we did well there. Perfect. And then the last thing here is just going back to what we said at the beginning when we started discussing inverse functions. The one requirement for an inverse function is that it has to be one-to-one. That's one thing we said has to be true. Because if it's not one-to-one, if you try to do an inverse, you end up with something that's not a function. And I'll leave it up to you to think about that and figure out why that's the case, why it has to be one-to-one for it to be a function when you switch the x's and y's around. But sometimes though we can do an inverse function with a function that's not one-to-one by using what we call a domain restriction. So as an example, it says find the inverse of x squared. Now we know earlier we did the horizontal line test and said that that's not one-to-one, right? That was an example we did earlier. So we're saying, okay, well, we want to go ahead and kind of pretend that it's one-to-one and see if we can find the inverse. The way that we pretend that it's one-to-one is we get rid of the part of the function or the part of the graph that makes it not one-to-one. And so that's what this piece right here is, where it says y is greater than or equal to 0. And actually that is a typo. That should say x is greater than or equal to 0. Okay, and what we're doing is we're basically taking that parabola. Let me see if I can do that here. Here is x squared. Of course, it's not one-to-one. But what we're going to do is we're going to basically get rid of the we're just going to get rid of the left half of the graph. And we're just going to get rid of the part of the graph that sort of offends us, you could say. If we start this out and we're going to make that go from 0 on up. So we're basically just looking at this part of the graph right here. Now that is one-to-one, okay? And so that's the part of the graph we're interested in, and that's what we have when this thing says if x is greater than or equal to 0, okay? So now we can say, all right, so it's one-to-one now, so the inverse function, if y is x squared, well then that means that x is y squared for the inverse, and we get that the square root of x is the inverse function. And we can take this then and do a square root of x. And if we just look at the x values that are greater than 0, do you see the symmetry? Okay, and you know we can probably do a little bit better. Just so we can get a decent picture of that symmetry there. And so there it is. For the positive x values, that is an inverse. Obviously for the negative x values, it's not going to be an inverse because you know, we can't really talk about those negative x values once we do the inverse, because for the square root of x, it just doesn't work out that way. Okay, so that's the end of that section. There's a summary of everything we looked at. That's in the notes if you want to review that. Otherwise, if you have questions, let me know.